Hey guys, this is Mr. Millings, and in part 3 of our 3-part series where we are learning how to calculate thermal energy changes when there is a change in state of matter, we are going to calculate some thermal energy when there are two phase changes. So these are typically going to be 6-step problems. So let's jump right in and take a look at our example here. It says to calculate the amount of energy in kilojoules that 75 grams of ice at -10 degrees must absorb in order to turn into water vapor at 125 degrees Celsius. So let's draw a little picture here. It tells us that we have 75 grams of ice, and this ice is at -10 degrees Celsius, and this ice is going to absorb some thermal energy from its surroundings. It's going to begin to heat up, and at 0 degrees Celsius, we know this ice is going to begin to melt. And if we continue to heat this water up, then we know at 100 degrees Celsius, this water is going to begin to boil. We're going to continue to heat this water vapor up to 125 degrees Celsius. We want to know how much thermal energy this ice is going to need to absorb to turn into water vapor. So the very first thing we're going to do here is we're going to figure out how much thermal energy the ice is going to need to absorb as it goes from -10 to 0. Once it hits 0, we're going to have to figure out the heat of fusion. That's the amount of energy it takes just to melt the ice. And our third step, what we'll have to do is figure out how much thermal energy this water here is going to need to absorb to go from 0 to 100. And our fourth step, what we're going to have to do is figure out the heat of vaporization. That's the amount of energy it takes to just convert water into water vapor. In our fifth step, what we're going to do here is we'll figure out how much thermal energy this water vapor is going to absorb as it goes from 100 to 125. Once we have all those numbers, we can simply add them up. So very first thing we're going to do here is we're going to take we're going to figure out how much thermal energy this ice here is going to need to absorb as it goes from -10 to its melting point. So our specific heat of ice, as we see right here, is 2.03 joules per grams degrees Celsius times the mass of the ice, 75 grams, times the change in temperature. The change in temperature here is going to be final minus initial. 0 minus a -10 is going to be a +10 degrees Celsius. We'll put this in our calculator. We'll take 2.03 times 75 times 10, and we will end up with 1,522.5. 1,522.5 joules. In step 2, what we need to figure out is our heat of vaporization, or our heat of fusion, sorry. So we have, let's see here, 75 grams of water. We know that 1 mole of water is 18.02 grams of water. And we know the heat of fusion of water is 6.02 kilojoules per mole. And this is going to be positive 6.02 kilojoules because it looks like our ice is melting. So it's absorbing energy, so our sign here should be positive. And so when we put this in our calculator, we're going to end up with, let's see here, 75 divided by 18.02 times 6.02. We're going to end up with 25.1 kilojoules. So now we need to figure out how much thermal energy this water is going to absorb as it goes from 0 degrees Celsius to its boiling point. So we'll use Cm delta T here. Our specific heat capacity of water is 4.18 joules per gram degrees Celsius times the mass, which is 75. This should say 4.18. There we go. The mass is 75 grams times the change in temperature. If it goes from 0 to 100, we take final minus initial, and we'll end up with 100 degrees Celsius. And so now we simply take 4.18 times 75 times 100, and we'll end up with 31,350 joules. In our fourth step, what we are going to have to do here is figure out our heat of vaporization. To get our heat of vaporization, we take the mass, 75 grams of water. We know 1 mole of H2O is 18.02 grams. And we know our heat of vaporization is 40.7 kilojoules per mole. And this will stay positive because the water is boiling. It's absorbing thermal energy and turning into water vapor. We'll get our calculator out. 75 divided by 18.02 times 40.7, and we end up with 169.4 kilojoules. In our fifth step, what we'll have to do now is we're going to have to figure out how much thermal energy this water vapor here is going to absorb as it goes from 100 to 125. Using Cm delta T, our specific heat capacity of water vapor is 2.0 joules per gram degrees Celsius times our mass, which is 75 grams, times the change in temperature. The final temperature is 125. The initial temperature is 100. Take final minus initial, and we will get 25 degrees Celsius. And so we'll put this in our calculator right now. And we end up with 3,750 joules. So now that we've done all 5 of these steps, we can add them up. However, some of these are in joules, some of them are in kilojoules, and so the question asks for our final answer to be in kilojoules. So we have to convert this to kilojoules by moving our decimal 3 times to the left. We'll end up with 1.5225 here. We're going to end up with 25.1 here. That stays the same. We're going to end up with 31.350. We're going to end up with 169.4 here. And we're going to end up with 3.75 kilojoules here. And so what we're going to do is we are going to add all 5 of these numbers up right here, right? We're going to add all 5 of these numbers up, and we should end up with our grand total of a positive 231.1 kilojoules. So that's how much thermal energy this piece of ice needs to absorb in order to go from negative 10 degrees Celsius to 125 degrees Celsius. It needs to absorb 231.1 kilojoules. This little positive sign right here, it means absorb, and this is going to be an endothermic process. If you like what you see, go ahead and click that little bomb in the bottom right hand corner. That's going to subscribe you to my channel, and feel free to leave any comments or questions in the comments section down below, and I really hope you guys found this helpful.